I'm going to cover a couple of physics demonstrations here that use bicycle wheels. One of the demonstrations is somebody sits in a spinny chair and they hold a bicycle wheel out in front of them, and then the bicycle wheel spins really fast, and then they can either reach out and grab that bicycle wheel or they can twist it in different directions, and then it causes the person in the it causes the person in the chair to spin in different directions. And then there's another demonstration where a bicycle wheel is hung from the ceiling and the bicycle wheel is spinning, but it doesn't fall over. So these demonstrations are often billed as scientific demonstrations, but they're usually more just parlor tricks because no explanation is ever given as to why things happen the way that they do. Sometimes people make vague statements such as conservation of momentum or precession, but you could also list off all of Newton's laws because they apply as well, but that doesn't explain anything. So in this video, I'm going to explain why these tricks work the way that they do, or why this demonstration works the way that it does. First off, I'm going to cover a person here, which is the black dot, sitting in a spinning chair, or a spinny chair that revolves or rotates around. Let's say they have a huge bicycle wheel in front of them. I'm exaggerating the size of the bicycle wheel for illustrative purposes. So the first demonstration is the easiest to explain. This person just spins the bicycle wheel extremely fast as they can. Then they have on usually a very thick glove, and they reach out and they grab that bicycle wheel to stop it. Think of the bicycle wheel as having a series of weights around the rim of it. Those weights you could imagine as being something like heavy cannonballs. So now you have this heavy cannonball right here opposite of this person. As soon as that person reaches out and grabs that wheel and stops it, this cannonball right here, or this weight, is going to want to continue going straight. This will cause the person to tend to spin counterclockwise. Notice the part of the wheel closest to the person will want to spin the person the opposite direction when they stop that wheel. But if you think of these distances right here from the person, this could be like the person catching something with a long stick. So imagine having a long broomstick with a net on the end of it, and there's a cannonball flying way out here. That person reaches out their stick with the net on it and they catch that cannonball. That cannonball is going to rotate them counterclockwise. There's going to be a lot of torque or twisting action right here from this long stick. But the mass on the near side of the wheel right here is going to have very little torque pushing the person in the opposite direction. So the mass on the far end of the bicycle wheel will win out because it has more torque. And as for the masses on the sides of the bicycle wheel right here, when that wheel is violently stopped, those masses will want to continue going straight ahead as well. Notice the mass right here will cause a twisting moment as well on this person in the spinning chair and want to cause this person to spin counterclockwise as well. And same with the mass on the opposite side of the wheel. But this mass will be wanting to travel forwards, and as it does, it will want to push this person counterclockwise. It looks like you could quantify this moment of torque right here by just taking the sine of this angle, because the longer this line is right here, then that means the farther out this mass will be, and the more it will want to push the person counterclockwise or rotate the person counterclockwise. Next up, I'm going to cover what happens when the wheel is suddenly twisted in different directions. For the next scenario, the red cup will represent the person in the spinny chair. The orange Araby frisbee thing here will be the bicycle wheel. This mass right here will be represented by the black mark on the Araby. So this could be like a heavy mass, like a cannonball or something. That's the way I think of it. So for the first scenario, this bicycle wheel is spinning very fast horizontally. It's like a cannonball traveling that way very fast. The person will suddenly flip the bicycle wheel up like this. That cannonball has to come to a sudden stop and start traveling upwards. So it's like reaching out with a stick, a long stick with a net on it, and catching that cannonball again. It will cause the person to spin, or it'll cause the wheel and the person in the chair to spin counterclockwise as we look down. The next scenario will be the opposite. If we have a bicycle wheel here, let's say that's spinning up like this. Here's the mass, and the bicycle wheel is vertical. Then the person suddenly twists the bicycle wheel from vertical to horizontal, so it's coming up this way. They suddenly twist it to horizontal. Now the mass will shoot off to the right, and then the equal and opposite force will force the person to twist to the left, which will be clockwise. So this scenario right here is like a person reaching out with a very long arm and throwing a cannonball to the right. So the counter force will push the bicycle wheel to the left and cause the person to spin clockwise. Next up, gyroscopic precession. Imagine you have a ball here or some sort of mass traveling along happily in a straight direction. You apply an upward force right here. It's not going to magically make the ball jump from here up to there, straight vertical. What it will do is send the ball off at an angle in that direction. So it'll go up and that direction. Same thing if these masses were attached to a wheel. Imagine the wheel just being covered with these masses. If you have a wheel spinning, what is that? Counterclockwise as we look down on it. If you have a mass right here on the near side and you push up on it, it's not going to push that mass directly up. It's going to push it up at an angle, so the whole wheel will tilt 90 degrees from us. And right there, so that's the mass that I circled right there. Now it's at the top because it got pushed up at an angle, the same way a ball would if we just applied a force to it while it was traveling linearly. And as for the gyroscopic precession about which I was speaking, let's say now we have a rope hung from the ceiling or a cord or whatever. It's attached to a bicycle wheel that's spinning. The top part of the bicycle wheel is spinning towards us. The bottom part is spinning away from us. Again, let's pretend there are masses on all sides of that bicycle wheel. The mass on the top of that bicycle wheel there is being pulled down by gravity, so it is getting a torque or a force pushing on that direction, trying to bring the top of the wheel down to the ground, but this bicycle wheel is spinning very fast. So before that mass could actually drop down to the ground, because the wheel is spinning so fast, really quickly that mass is going to go from the top down to the side right there. And as we just saw, if there's a force applied to a mass on a spinning wheel, then that force will cause the wheel to tilt 90 degrees from where the force was applied. So that means as this mass swings down and comes to the side right there, then that mass is going to be directed outwards. And this will cause the wheel to precess and spin the opposite direction. For example, the mass on the bottom of the wheel right here, or the bottom of the wheel, is spinning away from us, which means the bicycle wheel should spin towards us. But because of the gyroscopic precession of this mass being pushed out, now the bicycle wheel will precess away from us. And before I end the video, I'm going to include a bonus fact. Precession is different than procession. I just learned that during this project. Precession is what the bicycle wheel does. A procession is a line of people walking somewhere. I guess that might be a good example. But anyways, that's it.